Okay, we're beginning chapter 8, which is about confidence intervals. And a confidence interval is a range of numbers that's defined by a probability. So you've seen intervals before with histograms, right? So with a histogram, you had, all of these different classes. So with a histogram, so you had class number, and so maybe you had class number 1, class number 2, and class number 1 would be maybe from 0 to 10. And class number 2 would be from 10 to 20. So these were intervals. But this interval, which is a range of numbers between 0 and 10, for example, was something that we set or defined by calculating a width. But now a confidence interval is going to be a range of numbers, but it's going to be defined by a probability. And in the past chapters, chapter 6 and chapter 7, we've talked about probability being equal to an area, and an area under a distribution curve. So we're going to be using distribution curves in order to reflect a probability that will then be used to create an interval of a range of numbers. So we're going to be able to create confidence intervals around single population means and something called a population proportion. And we're going to be creating confidence intervals based off of the normal distribution. Remember that this is symmetrical and bell-shaped, right? Looks something like that. And there's a new distribution called the student's t distribution, which is symmetric, but it's not bell-shaped. It could be confused with a normal distribution, but its shape actually changes based off of the sample size. And we'll get to that. A population proportion, a proportion is a ratio or a fraction. So for example, if the percentage of people that would vote for candidate A in an election, is 60%, that would be 0.60. That's a ratio. So that's what we're going to talk about when we talk about proportions. And we're going to be creating confidence intervals based off of proportions here. All right, so there's 3 sections in this chapter. So let's start on the first one. This is just a summary, again, of what's in section 8.1. And we'll get to the meanings and uses of each of these formulas and equations and these ideas. So let's start with what we mean by a point estimate for a population mean. So in short, sample statistics can serve as point estimates for population parameters. So we can use a sample mean as a point estimate for an unknown population mean. We can use a sample standard deviation as a point estimate for a population standard deviation. And we can use a sample proportion as a point estimate for a population proportion. So, for example, I mean, this wouldn't be the most accurate thing, but, if we wanted to know, how many people were going to vote, in the next election for a certain candidate, and if we, had a sample of maybe 100 people, and of those 100 people, 60% would vote for candidate A, then we can say that this 60% proportion in our sample is a point estimate that the population at large is also going to vote for candidate A at 60%. And in terms of talking about um, point estimates between a sample mean and a population mean, we're using this symbol of mu hat to represent the point estimate. Okay, so the point estimate for the population mean is mu hat, and mu hat is equal to the sample mean. So we're just kind of using this symbol mu hat as kind of like an intermediary. Okay, it's a way to differentiate between a sample mean on one side and the population mean on the other side, and to say that each of those are kind of equal to this point estimate symbol. Now, we've seen this idea of point estimates before. So if you remember from the central limit theorem in chapter 7, we were dealing with a population, and we didn't know what the population mean was. But what we could do is we could take multiple samples and calculate sample means and take all of those sample means, and if we were to plot them, those sample means would create a normal distribution shape. And the center of that normal distribution shape is the mean of sample means, okay, which is the middle of that distribution. And this mean of sample means could therefore be used as a point estimate for the population mean that we didn't know at the very beginning. So we could kind of use this process of multiple samples in order to get this distribution so that we could get the center of that distribution and use that center as an estimate for the population mean that we needed to figure out that was unknown. So, here's an example using orange juice consumption. So if the orange consumption of orange juice for a random sample of 576 Americans was 133, so the average American drank 133 grams per day out of this 576 American sample. Give a point estimate for the population mean. So the average consumption of orange juice for all Americans. So the point estimate for the population is going to be equal to the sample mean. And the sample mean is 133. So that means the point estimate for the population at large is also going to be 133. All right, so that's it with the idea of a point estimate, how a sample statistic serves as a point estimate for a population parameter. Let me know if you have any questions.